Yeah, so you can start writing this on the column of 572. Were you able to get sine theta by itself to be negative 2/3? That would give you a reference angle of 0.73. Remember, when you find your reference angle, it would be sine inverse of positive 2/3. And so your answers would be in quadrants 3 and quadrant 4. Question number 2. 8 tan theta plus 3 equals 0. Again, solving between 0 and 2 pi. Able to get tan by itself, negative 3/8, get a reference angle of 0.359. Where is tan negative? Quadrant 2 and quadrant 4. 2.78, 5.92. In this case, you get cos by itself. Did you get cos equals 4? Is 4 on your unit circle? No. How can you do this without your calculator? It's not possible. That's how you can do it without your calculator. Why is it not possible? Well, cos is 4 over 1. Okay, draw a right angle triangle, label theta, label the adjacent side as 4 and the hypotenuse as 1, and tell me what's wrong. Right? If the cos is adjacent over hypotenuse and we have 4, you can't have a side length of 4 and the hypotenuse be 1. It's just not possible. So anytime for sine and cos that you get a value bigger than 1, it can be done without a calculator because you just have to recognize that and say it's not possible. Now so A through C were all review of stuff we did in chapter 6. We've solved before, we got reference angles, you can find out what quadrants are in. What's new in chapter 7 is this part right here. In question D, what happens if we didn't say our domain was just between 0 and 2 pi? In chapter 6, sometimes it went from negative 2 pi to 2 pi. In chapter 7, they just say, why don't we just let it go on forever? Why don't we include everything from 0 to 2 pi, but then 2 pi to 4 pi, 4 pi to 6 pi, and just keep on going? How would that change our answer? Well, what we're going to find is we're going to start by solving it exactly the same way. So we'll get tan by itself. This is a tricky one in that, do you recognize that value? Would you recognize it better if it was written like this? So sometimes we need to rationalize our denominator to be able to recognize that value's on my pi plate. What family is that? That's part of my pi over 6 family, and since tan is negative, it's in quadrant 2 and quadrant 4. Up till here, we have done exactly like we've done normally. I'm going to make a note here. All we did is we first solved it between 0 and 2 pi. Just once around the circle, we recognized the pi over 6 family and put the two answers between 0 and 2 pi. But we're not done this question because this question says you have to solve over all real numbers. So if we think about our unit circle, right, we know that one answer is here at 5 pi over 6, and one answer is here at 11 pi over 6. That's the first time around. But with all the real numbers, it says you can go around as many times as you want. So we could get to 5 pi over 6, we could add another 2 pi, and we'd end there again. And we could add another 2 pi, and we can end there again. And again, and again, and again, and again. So this is also connecting to something that you did earlier in chapter 6. in that, what do we call that when we list all the ones that end in the same place? We're listing all the coterminal angles. How did we do that? We could say, well, I could take 5 pi over 6, and I could add 2 pi as many times as I want. So 2 pi times k. You'll find that they put the k in between the 2 and the pi. But it's just 2 pi times k. And you do the same thing with 11 pi over 6. And you could leave your answer like this. So on the diagram off to the side, I've got a picture saying you could get to this one, and then in the green you could go all the way around again, and you'd get there again. You could go all the way around again and get there again. Those would be 5 pi over 6 plus 2k pi. The plus 2k pi lists all the coterminal angles with 5 pi over 6. Yes? So the difference between the z and the r, the z is just integers. And your real numbers is everything. 1.5, 1.72, all the decimals. So in this case, if I want the coterminal ones with this arm here, I can add 2 pi once, and it would end there. But if I add 2 pi a half time or 3/4 of a time, it doesn't end in the same place. It only ends if I add whole numbers or subtract whole numbers of 2 pi. And so that's why the z is there, because we're thinking of integers and not just any number. So this is perfectly fine, and this is a right answer. But some people notice a pattern with these two answers with tan. Do you notice that to hop from this one to this one is halfway around the circle? And to hop from this one back to this one is halfway around the circle? So sometimes you'll see the same solution written in an answer key like this. 5 pi over 6, start here. And if you add k pi, that's only jumping halfway around as many times as you want, and you would hit both of those at the same time. Now, for a mathematician, this answer is more simple looking than this answer. So this answer is nicer from a mathematician's perspective. It's important that you can see, now that you see them both, why they're the same. But when you're asked to write an answer, generally we'll do more like the top one. You'll find both of your answers first and add 2k pi to them. So this is what's new in Chapter 7. And if you turn the page to page 574, you've got some space in the top left-hand corner. And I'd like you to write out the steps for how we're going to solve what's called the general solution, where the domain is everything. In other words, the angle theta belongs to the real numbers. It means theta can be any number. So just like in the example we just did, step 1, you solve like normal between 0 and 2 pi. Once around the circle, find out all of your answers. And then once you've found those answers between 0 and 2 pi, in order to write all of the answers, you just have to write all the coterminal angles. And we've done this before. So each answer you add 2k pi to, where k is an integer. And then you'll be able to find them all. So the next thing I'm going to get you to do is put an X through question number 1. We're not going to do that one. We're going to do this one instead. Solve for theta, where theta is a real number. 7 sine theta plus 1 equals 0. So first of all, when we read the question, we recognize that it's a general solution question because the domain is given to be everything. So if we think back to what we just wrote, how do we solve a general solution one? Well, we're going to solve it like normal between 0 and 2 pi, and then we're just going to add 2k pi to each of our answers. So how would I solve this one like normal? Is that on my unit circle, 1/7? No. So we need our calculator. We need our calculator to find our reference angle. Then once we have our reference angle, what quadrants will this one be in? Sine is negative, so quadrants 3 and 4. So we can find if my reference angle is 0.143, then my angles would be 3.28 and 6.14. So then how do we write our final answer? We take our answers that we have between 0 and 2 pi and just add 2k pi. Did I write this as example A? Here, we'll call this A because we're going to do one more. But before we do B, I just noticed some very cool numbers and I want to tell you about them. This question happened, I think these exact numbers happened on a final exam. And after they made the final exam, I think they decided we should never ask this question with these numbers again. I'll show you why. So, go to our calculator. I'm going to open up a new page. First of all, to find your reference angle, the right way, you would do sine inverse of 1/7, right? So you take out your calculator and make sure that you're in radians. Second, sine inverse 1 divided by 7. 0.143. That's what we wrote for our reference angle. And the reason this question will never be asked with these numbers again is because when marking the exam, one student just went like this. So sine of theta equals negative 1/7. Sine of theta equals negative 0.143. What did that student do? They just did 1 divided by 7. Okay. 1 divided by 7 is 0.142857, which if you round is 0.143, which is really weird that the reference angle and the fraction, when you round to 3 decimal places, are identical. And so this person then next went sine inverse of my answer, and they're like, I basically got the same number twice, and they thought they did something wrong. I'm not doing something wrong. It is just a coincidence that 1/7 and sine inverse of 1/7 happen to be the same if you round to 3 decimal places. The 7ths are my favorite fractions. Is anybody else have a favorite fraction? No? Just me? Okay. Feel alone right now. I like 1/7 as a decimal is 0.142857 repeated over and over and over and over and over again, right? It's probably, usually, if you ask students which fractions they can convert to a decimal, they're like, you got 1/2, they're like, oh yeah, 0.5. 1/3, yep. 0.3 repeated, a quarter, yes, I have a quarter in my pocket, it's 25 cents. 1/5, ooh, a little bit of math, but yeah, like 0.2. And then they stop at 1/6, right? How are you? Is this you? Good? How about 1/6? No? Okay. 1/6 repeated. And just the 6 is repeated after that, not 1/6, just 0.16 repeated. It's half of 1/3, so you could just take all the 3's repeated and divide them by 2. And you get 1 and a bunch of 6's repeated. But then for sure you don't get to 1/7, which is the most fun one of all. Now, why do I like 1/7? Sorry, we'll get to example B in a second, but this is just such a nice fraction. It's cool that it has 6 numbers repeated. I think that's pretty cool. It's actually not too hard to remember those numbers, because if you just take 14, double it, you get 28. Take 28, double it, make a little mistake, you get 57. So it's not hard to remember the numbers. And then what's really cool about your 7ths, in my opinion, because it's my favorite fraction, I'm going to tell you what 2/7 is and what 3/7 is. And then you're going to, without your calculator, tell me what 4/7 is. So 2/7 is 0.285714 repeated. And 3/7 happens to be 0.428571 repeated. Your job is to tell me what 4/7 is. If you figure it out, don't yell it out right away to ruin it for someone else. So close, that's 5/7. No. Figured out 5/7. He's on to something. Okay, the person who said 0 point, good. Good work. Like it. The first one's 5. Yes, but not 6. 5/7, and then? Good. Notice the original numbers, 142,857. The second biggest number is a 2. And then the order stays the same, 285714. Then the third biggest number is the 4. And the order stays the same, 428571. Then the 571428. What is 6/7? 0.857142 repeated. Anyways, I think that's super cool. I like finding interesting patterns in numbers, and 7s are my favorite. Anyways, all because I chose 1/7 for that question. We'd be done class so much earlier if I'd picked an easier number. But it wouldn't be as interesting. Find the general solution. So sometimes they tell you the question will have the domain listed like this. And sometimes the question will just say, find the general solution for 5 cos theta plus 1 equals 0. So again, I want you to try this one on your own. I'll put the answer up in a bit. I didn't show any of the work. You had to get your own reference angle. It's negative, so it's in quadrant 2 and quadrant 3. .51. Yeah, it doesn't look like a 5 or a 9, I don't think. Questions? Did you get the right reference angle? So were you able to get cos by itself? -1/5. Were you able to get your reference angle? Okay, this is where people make mistakes, is they do the reference angle with a negative, but the reference angle is just cos inverse of 1/5, 1.37. Reference angle, 1.37. How do I find an answer in quadrant 2? In quadrant 2, I would go pi minus my reference angle, 1.77. How do I find my answer in quadrant 4? I'd go 2 pi minus my reference angle, 4. Oh, it is a 9. Yeah, this obviously doesn't look like a 9 either, but maybe, no, it's just bad. 4.91. Oh, yeah, part C. Yes. Oh, and it is 4.Y1. Yes, cos is negative, quadrants 2 and 3. So if we, oh, this is nasty. If we go pi plus our reference angle, it is 4.51. Okay, let's try to replicate that 5. Was that like bad like that about? Okay, perfect. 4.51. Yes, because cos is negative in quadrant 2 and quadrant 3. All right. Third example, last one for this. Solve for theta. This is the third way a general solution could appear. They try not to do this, because normally students look for the domain. Do you see how the domain isn't listed at all? It just says solve for theta. Now, technically, when something says solve, it means find all the answers. Don't just find some, but find them all. So if something says solve and they don't give you the domain, you have to assume it's everything. So we'll just write that in a different color here. Now we have a quadratic equation. Tan squared plus 3 tan theta minus 7 equals 0. And it's a trinomial. So this normally gets you to the point where you say, I should try to factor this. Now, if you tried to factor this, you would put your two things equal 0. The only way you could get tan squared is tan and tan. So it seems like things are going well for your factoring. What's the only way to get 7? This isn't hard either. 1 and 7, right? No other whole numbers multiply to 7. So we got 1 and 7. Now when we try to do our plus signs and minus signs, does the outside and the inside ever make 3 with 7 and 1? No. So at this point, we find out it can't be factored. What did you do in grade 11 when you were trying to solve an x squared equation like this, x squared plus 3x minus 7 equals 0? Here. We'll, here, off to the side, translate it back to grade 11. If you had to solve that quadratic equation and you couldn't factor it, What did you do in grade 11? You either completed the square or the quadratic formula. You had to use one of those things, right? Okay? If you look at your formula sheet in grade 12, the quadratic formula is on your formula sheet. If it's on your formula sheet, that means it's fair game to add to any question. In fact, they only added it to the formula sheet, like the original formula sheet came out with the new course, and then 2 years later they added the quadratic formula, and then they started asking these questions on the final exam like crazy. So I think they've calmed down a little bit, but it's very typical to get a question like this. So your quadratic formula looks like this. On your formula sheet, for ax squared plus bx plus c equals 0, x is equal to negative b plus or minus b squared minus 4ac over 2a. Oh, I'm really curious if it has that first part on there exactly like I wrote. Yes. I just missed one thing. On your formula sheet, there's a comma. But other than that, it's the same. So for ax squared plus bx plus c equals 0, x equals that. What do we have? We don't have x squared. We have tan squared. Okay? We have a number in front of tan, which is like there's a 1 there even though it's not written, right? So a is 1, b is 3, c is negative 7, but instead of an x, we have a tan. So when we go to use this formula, instead of writing x equals, we will write tan theta equals negative b, negative 3, plus or minus b squared, which would be 9 times 4. A was 1. C was negative 7. Correct, or positive 7? Nope, negative 7. All over 2 times A, 2 times 1. Now, if we simplify this equation a little bit, we get tan theta equals negative 3 plus or minus the square root of 9 plus 28, 37, all over 2. Is that on your unit circle? No. With the plus or minus, at this point, it makes sense to separate it into 2. We would have one side where you'd use the plus sign, negative 3 plus the square root of 37 over 2. And the other side where you'd use the minus, negative 3 minus the square root of 37 over 2. And as we get into higher level mathematics, these are the kind of things that come together, okay? We have concepts from before, like the quadratic equation, appearing with a concept that we have right now, solving for theta. We get more complicated looking data, but you have to take a step back and say to yourself, how do I solve for theta? Do I remember all of the ideas involved with solving for theta? What do I have to do? I have to get a reference angle. I have to know what quadrant it's in, and then I can solve for theta. So we're going to do the same thing for both of these equations. We're going to find a reference angle. We're going to find our quadrants. And then we still have to write the general solution in the end, because this question said solve for theta over all numbers. So first of all, when you look at this, can you tell which quadrants it's supposed to be in? Or does it look a little complicated? Looks a little complicated. So what I might do is I might go to my calculator and I might write this fraction in, negative 3 plus the square root of 37 all divided by 2, and just find out that it's equal to 1.54. I might even write this out underneath 1.54 dot dot dot. That's a lot easier to tell that that's a positive number than negative 3 plus square root of 37 over 2. So right now, I can put a little note here. I know this is going to be in quadrant 1 and quadrant 3 because tan is positive. I can find my reference angle. Okay, go to my calculator, go tan inverse of that answer, and I can find my reference angle is 0.995. Now that we know our reference angle, we can solve for theta between 0 and 2 pi. It's going to be in quadrant 1, which is 0.995. And in quadrant 3, so go back to my calculator, quadrant 3 would be pi plus my reference angle, 4.14. Those are my answers between 0 and 2 pi. Maybe I'll put that in brackets underneath. Those two answers are between 0 and 2 pi. So if I wanted to find my general solution, all my answers for this side of my equation, theta would equal 0.995 plus 2k pi and 4.14 plus 2k pi. So we solved one side of the equation. If we look back at what we did, even though the numbers weren't nice, we had to keep the idea of how do you solve for an angle. How do I solve for an angle? Well, I need a reference angle, and I need my quadrants. And then because it's quadrant 1 and 3, quadrant 1 is going to be the same as my reference angle. Quadrant 3 is going to be pi plus my reference angle. Those are my two answers between 0 and 2 pi. If I want a general solution, I add 2k pi to each of them. We're going to do the same thing on the other side. We're going to first go to our calculator and see what happens if we write negative root 3 minus the square root of 37 all over 2, negative 4.54. Again, not on our unit circle. But now our answer is negative. So we need to find our reference angle. Okay? Our reference, so we know that this is going to be in quadrant 2 and quadrant 4. When we do our reference angle, we always go tan inverse of the positive value. So if I go tan inverse and I want this number to be positive, if I just use the answer, can you see that the number there would be negative? How can you make a negative number positive? Multiply it by a negative 1. To get my reference angle to be 1.35. Okay? Some other things, sometimes people just go tan inverse and they just write it all in, 4.54138 1265. Notice that we get the same answer if we do that. Sometimes if you type it in, because technically you are rounding at this last digit, sometimes the last couple of numbers might be different. In this case, they're the same. So technically it is better if we can use the values that are there, because it's the calculator's actual values remember more digits than we can see. But in this case, it comes out to be exactly the same. Now that we've found our reference angle, okay, we want to find an answer in quadrant 2 and quadrant 4. If you have this calculator, another thing that can sometimes really be helpful on a graphing calculator, right above your on button is a store button. If you hit the store button, it says, where would you like to store your answer to? You can use any of the letters that are there. I like to just use this X button because it's really quick and easy to push. So then your calculator stores that number as X. Why is that helpful? Well, if I want to find my actual angle in quadrant 2, I have to do pi minus my reference angle, but now it's stored as X. I can just go pi minus X, push enter, and I get my first answer, 1.78. And in quadrant 4, I can go 2 pi minus my reference angle, and since it's stored as X still, I can just go X, 4.93. Again, I'll make a note. I'm going to cheap out and make an arrow so I don't have to write as much. Those are answers between 0 and 2 pi. So if we want to write all of our answers, we take our answers between 0 and 2 pi and add 2k pi where k is an integer. So technically, the only new thing we did today was the plus 2k pi. That being said, reviewing the quadratic formula with a tan function, that might have felt new. But it's something you've done before. So if we look at this whole equation right from the beginning, wow, we wrote quite a bit. It's kind of tiny when you see it all at once. We saw a quadratic equation that triggered in us the feeling like we should factor it. But we tried to factor it and it didn't work. So then we thought, what are ways that we could solve this without completing the square quadratic formula? The quadratic formula is on our formula sheet. Wrote it out and said, okay, can I apply the quadratic formula to my equation? That gave me 2 equations for tan. I wrote them out separately. And even though the numbers weren't pretty, the process for solving for an angle stays the same, with nice numbers or not. You need to find your reference angle, you need to find out what quadrant it's in, and then write your answers. Now we wrote our answers, and most students will stop right at this green line here because you're like, I've got answers, I'm going to move on. But if we go back to the original equation, we're solving for the general solution. We're not done yet. The general solution says solve first between 0 and 2 pi, then add 2k pi. That's what's new for today. So when you do your test on chapter 6, there won't be any general solution questions. All of chapter 6 will say solve between 0 and 2 pi or negative 2 pi and 2 pi. They'll give you a domain. Chapter 7 adds the general solution, but this is the only thing that's new for today. Okay? So questions to try. 5, 6, and 9.